Let's start by predicting the hybridization and geometry around each indicated atom. So we're pointing to the carbon here. It has 3 sites of bonding. There aren't any extra hydrogens on this carbon, just because it already has 4 bonds. Therefore, it must be sp2 hybridized. And that also means it's trigonal planar. Okay. If we look at our next one, we're talking about this nitrogen. It has a lone pair of electrons we can't forget about. So it is sp3 hybridized because it has 4 areas of electron density. Therefore, it is tetrahedral. If we look at our next atom, we're considering this carbon. It has 3 areas of electron density. Therefore, it must be sp2. It is also trigonal planar. I'm just going to shorten that for the time being. Trigonal planar. This carbon right here has 4 areas of electron density. Therefore, it is sp3 hybridized and tetrahedral. This oxygen, draw in its lone pairs. It has 3 areas of bonding, 3 areas of electron density, I should say. Therefore, it is sp2 hybridized. And all sp2 hybridized atoms are trigonal planar. All right, next step. Label 5 polar bonds with delta plus and delta minus. Okay, I'm going to start with this bond. Anytime you have a bond with 2 different atoms attached, you're going to have a polar bond. Oxygen is more electronegative than carbon, therefore it has a delta minus. Carbon has a delta plus. Let's look at this carbon-hydrogen bond. There are definitely more than 5 polar bonds in this compound, so you could pick many of them. This carbon is more electronegative than hydrogen, therefore it has a delta minus relative to hydrogen. Hydrogen would have a delta plus. Just considering this hydrogen-carbon bond. Let's look at this carbon-oxygen bond. Again, oxygen is more electronegative than carbon, therefore it has a delta minus. Carbon of the carbonyl has a delta plus. Let's look at the sulfur-carbon bond. Sulfur is more electronegative than carbon, therefore you have a delta minus on sulfur, delta plus on carbon. Let's choose one more. How about the carbon-nitrogen bond? Nitrogen is more electronegative than carbon, therefore delta minus on nitrogen, delta plus on carbon. Draw a skeletal structure. All right, I'm going to go ahead and start with the ring. So all hydrogens are implied except for the ones on heteroatoms. So let's start with the ring. Aromatic system. Draw in the pi bonds. Draw in the alcohol. So there's the alcohol. Here's your ring. Opposite of that alcohol is now this carbon. We can draw that as a straight line. And we have a nitrogen coming off of it, an NH2. We have to write those 2 hydrogens because nitrogen is in carbon. So anytime you have a heteroatom, you have to indicate how many hydrogens it has, just like with the oxygen here. Coming off of this carbon is this carbonyl. Anytime you have a vertice, that's a new carbon. This carbonyl is attached to an NH. Again, we have to draw on that hydrogen. Then we come down to a 4-membered ring attached to a 5-membered ring. I'm going to draw the 4 first. And in that 4-membered ring at this vertice is a nitrogen. And here we have another carbonyl. We can ignore these two hydrogens because they're attached to carbons. Now let's finish off our 5-membered ring. There's a sulfur at this vertice. We have 2 methyl groups here. Hydrogens are implied. And we have our carboxylic acid on the end. All right, that is the skeletal structure of amoxicillin. Label all of the pi bonds. I'm going to go ahead and just label them on this compound because I've kind of run out of space over here. Let's go green. Label all the pi bonds. Pi bonds are always double or triple bonds, and they're always made up of p orbitals, just as an FYI. So I'm just going to overlap all of the pi bonds or all of the double bonds or triple bonds in green. So pi bonds are in addition to sigma bonds. So the entire double bond isn't a pi bond. It starts as a sigma, and the more bonds you add, each additional bond is a pi bond. So for instance, here, one of these bonds is going to be a sigma. The additional one is going to be a pi. Doesn't matter which is which. It's just how you want to draw it. Just recognize that one is a sigma and the other is a pi. So I believe these are all of the pi bonds within amoxicillin. Find a CH bond containing a carbon atom having a hybrid orbital with 33% S character. Okay, let's see if we can do this. So, a hybrid orbital with 33% S character. Well, we know we typically have 1 S and 3 P's that we can overlap in order to form hybridized orbitals. These p orbitals are taken away to form pi bonds in certain cases. So for instance, this carbon has a pi bond. This pi bond would be taken up with a p orbital. All that's left over is an S and 2 P's to hybridize. That's officially why this carbon is sp2 hybridized. So we need to figure out what it's going to take for the overall hybrid orbital to be 33% S. If we combine all 4 of the orbitals, well, sp3 is going to be 25% S, and 75% P. Well, that won't do it. What if we try maybe sp2? sp2. So 1 S and 2 P's. That'll do it because a third of the overall orbital has S character. 33% S and 66% P. So we are looking for a carbon-hydrogen bond where the carbon is sp2 hybridized, because that's how you're going to get an sp2 orbital to overlap with the s orbital. So you want to look for any carbon that's sp2 hybridized and bonded to a hydrogen. I see 4 of them right away. And they're all on this benzene ring. So each of these 4 carbons is sp2 hybridized, and it has a hydrogen attached to it. Just looking right away, I don't see any other bonds that would count, and I think it's only those 4.